Hi, I will present our work, Analysis of the Frequency-Dependent Lumped Parameter Transmission Line Model. First, I will talk about transmission line representation and the frequency-dependent lumped parameter model. Then I will present the objectives of our work, the proposed methodology, results obtained, and finally, conclusions. The transmission line can be described as longitudinal parameters, which are the resistance, the inductance, the capacitance, and the conductance. One approach to represent the distributed nature of the transmission line is by lumping the distributed line parameters into line sections. The classic lamp parameter model represents each section by a pi circuit. Each pi circuit divides the transversal admittance of the transmission line into two shunt circuits that are placed at the beginning and at the end of each pi section. The longitudinal parameters is placed between both shunt admittances so that each pi circuit is as the one shown here at the right of this slide. An update to the lamp parameter model is the frequency-dependent lamp parameter model. Here, the rational functions and equivalent circuits are used to represent the frequency dependence of the longitudinal parameters, as that can be seen at the bottom of this slide. The state equation that describes the frequency-dependent lamp parameter model can then be written and directly solved in the time domain by using numerical methods of integration. One issue with the previous representation of this model is that it has only been described for two scenarios, that is, open circuit test and short circuit test. That is why in previous representations, input vector U contains only the voltage at the sending terminal of the transmission line. And from this model, the only possible outputs are the input current, the output current, and the output voltage, as you can see in output vector Y. Thus, the objective of our work is to present the generic state space model of the frequency-dependent lumped parameter model, show that the frequency-dependent lumped parameter model is accurate when compared to the J-Mardy line model, both in the frequency domain and in the time domain, show how the number of lines, sections, and the quality of the feeding affect the performance and accuracy of the frequency-dependent line parameter model. To represent the frequency dependence of the longitudinal parameters, we use vector feeding to feed the longitudinal impedance to a rational function. Then the residues and poles of the rational function are associated to an equivalent circuit. This circuit is placed in each frequency-dependent pi section so that the cascade of the frequency-dependent pi section is the one shown at the bottom of this slide. We present the generic state space formulation of the frequency-dependent lamp parameter model, which is composed by matrices A, B, C, and D. Details about each matrix can be found in our paper. The objective of our work was to present the generic state space representation of this model. As a result, we have as inputs the current at the input terminal, the current at the output terminal, and we expect from this model the voltages at the receiving and sending terminals of the transmission line. To show results, we simulated transmission line shown in this slide, and we calculated the longitudinal impedance as a function of the frequency. We can see here that a rational function fitted with two poles can only represent the longitudinal impedance up to 1 kHz. in both graphs, both in the resistance and the inductance, we can see that the rational function fitted with 6 poles, it can represent up to 10 kilohertz. But only a rational function fitted with 10 poles can represent the longitudinal impedance with little error up to 1 megahertz. In the frequency domain, we compare the frequency-dependent lamp parameter model to two other well-known models. The first one is the analytical frequency domain solution of the transmission line, which is the blue solid line. We have here the both diagram for all models, and we compare the analytical frequency domain solution of the transmission line to the GMRD model and show that the GMRD model does not represent the transmission line perfectly. We also presented how the frequency response of the frequency-dependent lamp parameter model varies as a function of the number of poles used to feed the longitudinal impedance and as the number of cascaded elements used to represent the transmission line. We can see here, for example, that a transmission line that is fitted with 4 poles and that has a cascade of 10 frequency-dependent pi sections can only represent the transmission line up to 10 kilohertz. As we increase the number of frequency-dependent pi sections and the quantity of poles used to feed the longitudinal impedance, we can see that we can accurately describe the ratio between the input voltage and the output voltage of the transmission line. Now, in the time domain, we simulated both models, the GMRD line model and the frequency-dependent lamp parameter model, for various scenarios. Here, in this slide, we can see 2 scenarios. The first one is an open circuit transmission line that has a 1 pu DC voltage source at the sending end of the transmission line, and we can see that the voltage that the curves obtained with both the GMRD model and the frequency-dependent lamp parameter model are basically the same, with almost no error. We also simulated a high frequency transient, which is when we simulate a 1.250 microseconds current source at one of the terminals of the transmission line and leave the other terminal open circuited. We can see at the bottom of this slide that the curves obtained with both models are practically the same. This indicates that the frequency-dependent lamp parameter model is accurate for the representation of both low-frequency and high-frequency transients. Since the objective of our work was to present the generated state space representation of the lamp of the frequency-dependent lamp parameter model, we presented the generic state space equations of this model. And to show the capabilities of this model, we simulated the following scenario. We connected a AC voltage source to one terminal of the transmission line and connected a diode in series with a resistor to the other terminal of the transmission line. As expected, we can see here that the voltage at the receiving end of the transmission line has both positive and negative semicycles, whereas the current has only the positive semicycle. This can be also used in another simulation that contain nonlinear and time-dependent devices. Finally, we presented the generic state space model of the frequency-dependent lamp parameter model. So this model is now not only limited to the simulation of short circuit and open circuit tests. We also compare the performance of the frequency-dependent lamp parameter model to other accurate time-domain transmission line models, and also with the analytical solution of the transmission line, we made the comparisons both in the frequency domain and in the time domain. Results show that the frequency-dependent lamp parameter model is accurate and can be used for the accurate simulations of the transmission lines. Thank you very much for your attention.
Hi everyone, it is a great pleasure to be participating in this conference. I would like to thank for the organization for making it possible to happen during these tough times, and I would also like to thank for the audience that is attending to this workshop. So our work was entitled as a generalized power grid reduction technique that was developed by me, by my colleague Victor, and by our professors and advisors Anésio Giledes and Josh Kurmani. So as an introduction, I would like to present the motivation of our work. So it was requested a robust circuit reduction technique to be applicable to distribution system studies. So for this reason, it was necessarily to take into account some inherent characteristics of distribution systems as multi-phase lines, unbalanced loads, different topologies, and eventually some load variability throughout the day. So in order to cover all these requirements, our formulation was based on primitive admittance metrics. So by taking a look on these three buses with multi-phase lines, we can see how the primitive admittance metrics are built. And by using those primitive admittance metrics, we are able to build our full admittance metrics that will describe the entire system. And by using the full admittance metrics, we are now able to derive for our reduction formulation. So let's say that we were trying to remove the bus 2 out of the system. So this would be the inner bus removal case. So here we have how would be the equivalent line parameters, and here we have how would be the load allocation factors that would be responsible to place the load from the bus 2 into its adjacent buses. Here we have a terminal bus removal case when we would be interested to remove the bus 3 out of our example system. So I would like to present the weight matrix concept. So for each bus elimination, we are not placing the load on its adjacent buses right away. Basically, what we are doing is that we are computing the load allocation factors, and then we are placing all those allocation factors into the weight matrix. So by the end of the overall reduction process, we are going to be able to place all loads from the original system directly into the buses that remaining on the reduced system. So now I'm going to present it to you the overall reduction process by taking and using these 10 buses meshed feeder as an example. So for the initialization process, the user will select all buses of interest to be retained on the equivalent system. Therefore, we're going to import all the lines parameters. We're going to also import the loads as a vector array, and then we're going to perform the topology detection, and the topology information will be placed into a incidence matrix. So this incidence matrix will allow us to manage and update the topology of the system accordingly. So after all data imported, now we're going to perform a auto bus selection that will select all derivation buses of the system. So derivation buses are buses that are connected with more than 2 branches. Also, we will auto select some buses that are connected to special elements as transformers, regulators, generators, inverters, and others. So now our system is ready to be reduced. And now we can note that we have one terminal bus passive of reduction and also one inner bus passive of reduction. Let's start by a terminal bus elimination. So basically, we compute the load allocation factor that will be responsible to place the load from the terminal bus into its parent bus. We remove the respective branch, we compute the equivalent line, and then now we can note that this bus is no longer a derivation bus anymore, and now it's passive of reduction. So here we have the inner bus elimination case, where for this case we compute the load allocation factors that will place the load of the respective bus into its both adjacent buses. And then we compute the primitive admittance matrix, and now we have the equivalent system. So what if would happen if the user has not selected any buzz in the initialization process? So we would have 2 more buzzes passive of reduction, then we would repeat the overall process again, and we would converge to a parallel branch. So note that this case only occurs when we have a meshed topology. Basically, we merge all the line parameters and we continue with our reduction process. And here we have an equivalent 3 buzzes reduced feeder of our 10 buzz example. On this flowchart, it basically summarizes all the steps that are just presented to you. It's important to mention that this closed loop guarantees the maximum reduction capability of our technique. And then we can take a quick look and then we can go over to the results. So for the results, we choose a IEEE 123 node stats feeder system, mainly because of these unbalanced characteristics. So rather than using a voltage magnitude difference, we choose to use a phasorial relative error in order to make our evaluation more accurate, and also by indirectly evaluate the unbalanced conditions of the systems. So for our first study case, we performed a reduction rate sensibility analysis where we reduced the same system by steps of 5%, and for each step we evaluated 500 times, and then we took the average values and plotted on this chart. So we could achieve a high accuracy, and the simulation time was 63% faster. For our second study case, we evaluated the robustness of the reduction technique for different topologies. So here we have a radial feeder, and by closing some normally open switches, we can achieve a meshed feeder. So here we have the equivalent radial feeder with 13 buzzes, and here we have the equivalent meshed feeder with 16 buzzes. And here we have the results. So we can see a slightly higher difference for a radial topology that can be explained due to the higher reduction capability of the system in comparison to a meshed system. For our next study case, the proposal was to verify the capability of the technique for a time series simulation, and then we evaluate the losses throughout the day. For this case, we used a modified test system with some PV penetration. So on the right-hand side, we can see the equivalent circuit diagram, and then we can note on the chart that the higher variations are observable when we have a higher loading condition on the system. So our last study case was done with the purpose to evaluate the technique in a real high-dimension complex system, and for this reason, we choose an ePRI M1 test feeder system. So here we could achieve a high accuracy as well, a high dimensionality reduction too, and the simulation time dropped 3 times. So in order to conclude, I would like to highlight the contribution of our work. So it was developed a power system reduction technique applied to radial and non-radial topology grids that it's also applicable to multi-phase unbalanced systems modeled with neutral wire. I would also like to mention some advantages of our work that presents a high voltage accuracy, a significant simulation time reduction, is essentially independent of the load operation point. It's applicable to power flow and to dynamic simulation that allows us to make some fault studies. So thank you for your time and have a good day.
Hi, my name is Caio Messiaja, and I will present article entitled Electromagnetic Interferences Between Power Lines and Pipelines Using MTP Techniques. Case of electromagnetic interferences between transmission lines called source circuit and pipelines called target circuits in the same right-of-way have become more frequent and complex due to industrializations of the countries and the increasing of the restrictive environmentals. As a consequence of electromagnetic interferences, risks to the facilities and people involved may appear, and it is necessary to predict these risks and make the facilities safer. This work presents an improved model to predict the effects of induced voltage in steady-state regime with arbitrary geometry composed by obliquities, crossings, and parallelisms. Similar studies using MTP techniques has been reported in the literature. However, these studies uses simple geometries composed only by parallelisms or only by crossings. In real case, search and target secret paths sharing the same right of way are not completely parallel, since there may occur obliquities and crossings between the facilities. For this reason, in this model, the target sequence is subdivided and is approximated by equivalent parallelisms with equivalent lengths and equivalent distances. The subdivision points make each region's boundary determined from the intersection of the projections of the circuit line towers with the closest point to the target circuit. In case of obliquities between the circuits, the equivalent distances can be calculated by the square root of the distance 1 and distance 2, and the distance 1 and distance 2 rate needs to satisfy this condition. If this condition is not satisfied, the oblique segment is subdivided in two or more equal until it is met. For crossings, a circumference with 10 meters radius is centered in the crossing, and the intersections with the intersections with the target circuits determines the distance 1 and distance 2. The equivalent distance 1 and equivalent distance 2 can be calculated with the half of the distances respectively. For each couple region, the proposed methodology used a P model, which self and mutual impedances are calculated using the power series expansions of the Carson's formula. To test the model, one hypothetical case is studied. The system is composed a three-phase untransposed transmission line that operates at 115 kilovolts, single circuit, and triangular phase conductor arrangement. The line is energized with 830 amperes per phase, ABC sequence, and 60 Hz. An underground carbon steel pipeline buried at 1.5 meters deep and with 16 inches diameter shared the right-of-way with the transmission lines. These figures represent the XY plane, which shows a perpendicular crossing between source and target circuit. These figures show the induced voltage along the pipeline, and the results obtained using the proposed methodology are compared with the results of the right-of-way software. Consider the induced standards for the calculations of electromagnetic interferences. The error is calculated as the normalized root mean square deviations, which represents the overall discrepancy between the responses. The responses obtained by the proposed methodology are in accordance with the reference software and accurate, present discrepancies of 4.36% between the responses. Considering this scenario, the maximum voltage induced in the pipeline is 18 volts, which violates the 15 volt safety limit established by NACI. To reduce the induced voltage, it is chosen to use ground resistance at the pipeline ends. These figures show the induced voltage along the pipeline for different ground resistance values. This figures shows which the induced voltage vary according to the value of ground resistance employed. And using a ground resistance of less than 1 ohm at the ends of the pipeline, the induced voltage meets the safety criteria established by NACI. So, these works present the main innovation. The main innovation of this article was the subdivision technique employed to represent arbitrary geometries in terms of equivalent parallelisms. And one hypothetical case is studied, and the proposed methodology is valid and results has excellent precisions, with less than 5% discrepancy with the industry standard software for electromagnetic interferences. Strategies to mitigate the risks to which the pipeline was posed are analyzed, and 1 ohm at the ends of the pipeline was effective to reduce the original volts, and approximately 50% make it the facilities according to the safety criteria adopted. So I appreciate your attention and I appreciate your time. Thanks and have a good time.
Hello everyone, my name is Jonas. We have made a study case of the maximization of revenue of hydroelectric power plant in the context of the future power market of Brazilian power system, which will bring this possibility to operate using our price of electricity. The presentation outline is as shown in slide 2. First, I will speak about a little bit of the technical aspects of Itaipu power plant. Then we'll speak about the concepts that we use for maximization of the revenue of power plant on Brazilian power market. Then I will show the method that we used, and also I will speak about the development that we made. I will show some results and the final considerations of the study that we made. Itaipu power plant is a power plant located at the border between Brazil and Paraguay, and we have 20 generators of 700 megawatts. So we are able to generate the maximum of 14,000 megawatts, which is our installed capacity. We have 2 substations, 26 main transformers, 12 transmission lines, short transmission lines, and our dam have 196 meters height, and our spillway is able to spill as much as 62,000 cubic meters per second of water. To generate all that capacity, there is main process of our company. Most of them from the operation point of view are shown on this slide, which is the team that determines the water availability made forecast that we use to know how much water we have to generate. There is a process of coordination of maintenances, which tries to put the equipment on maintenance where there is no water available. There is a team and a process to determine the transmission capacity, which involve simulations and the solving of several dynamical phenomena, and also a team that tries to coordinate our generation with the load of the load center. Itaipu has been operating for more than 30 years, and we gathered some experience on the field and improved those processes that I just have shown. Thus, we have also raised our performance, which is the ratio of our equivalent production and our feasible production, reach as much as 90% and above 90% in most of years in the last years of our operation, which are the numbers that are shown in red on this slide. The market rules that are in Brazilian power markets are somehow changing. There is an effort to bring in 2021 the hour price for electricity, and this hour price for electricity will bring some opportunities for power plants to sell the surplus of the long-term transactions on this short-term electricity market. So, in this context, what we have today is that the operators negotiate the fulfillment of the schedule with the NSO of the Brazilian power system, and we are trying to bring this new type of operating, which is to negotiate the goal of generation that we can bring using information of power market. So we develop a routine that considers short-term price for maximizing revenue, and it is based on an optimal power flow solution to maximize the revenue considering the price, our price of the electricity of our market. Using this information, which is called in Brazil the shadow price, which is the precification without the operation of the price. We have this information already. We make this study and we gather some results. In this slide for the September 19th, the last September 19th, we had obtained a gain of 4.3%, just to illustrate the results of our routine, and which is considerably significant, because when we talk about the generation of entire power plant, it can be significant amount of money. One thing that we saw also is that the shape of generation can change significantly. In this slide, in the light gray, we have the schedule for that day, and in dark gray, we have the optimal generation. So we can see there is a significant change in the shape of the curves. Mainly, the shape of the optimal generation is get closer to the shape of the pricing of the day. So, based on this study that we have made, there is a few power market changes occurring in Brazilian power system, which can bring some opportunities for raising the revenue of power plants. Using this type of proposition that we made in the paper, we can increase as much as 5% of the revenue, which is considerably significant. And for this to be operation, we are aiming to do an application that is compatible with a supervisory system. then we can bring it to the operators. Thank you all, and especially the organizing committee of the workshop on communication networks and power system. Bye-bye.